Hello everyone, my name is Zawad and in this video I'll show you how to make sodium chloride crystals at home. In today's video, I'll look into the process to make FCC or face-centered cubic sodium chloride crystals at home, and I'll show you the results I obtained. We will also have a brief look at the physics at work here and discuss the factors that affect crystal formation. So, what do we need to make the crystals? On the screen now you'll see a list of stuff needed. Our primary ingredient is non-iodized or uniodized table salt. It is important that it's uniodized, as presence of any iodine ions would disrupt the cubic crystal formation. If your aim is not to form perfectly cubic structures, you can go ahead with regular table salt. Besides that, we need a pot to heat water, something like a spoon to stir, filter funnel and filter paper, a large jar, some flat dishes, and containers like petri dishes to grow the crystal in. The procedure is easy enough. Step 1 is to make a supersaturated solution. As solubility of salt increases with temperature, we heat water up in a pot, add salt and stir. We keep adding salt until no more salt dissolves. Then increase the temperature some more and repeat. We do this till we reach temperatures near the boiling point. Addition of salt is stopped only when no more salt dissolves. The solution is then transferred to a plastic or glass container and left alone for 1 or 2 days. After that, the solution has cooled down and the excess salt and other impurities have settled near the bottom. Through the filter paper and funnel, the solution is then transferred to a clean, dry jar. Now that we have our saturated solution, we need to grow a seed crystal. A seed crystal is a tiny, perfect sodium chloride crystal that we can then use to grow a bigger crystal. It's easy to grow seed crystals. Just pour 50 milliliters of the solution we recently prepared into a flat dish. We don't need to fill the dish, the solution just needs to be around 1 cm deep. We now leave it undisturbed for 1 or 2 days. After the formation of seed crystals, we transfer a decently sized crystal into another clean and dry flat dish like a jar lid. Transfer some of the solution there and leave it undisturbed. The longer it is kept undisturbed, the larger the crystal will grow. Our word of caution: if the solution is not saturated, the seed crystal might dissolve. Here, you can see the crystals I obtained. The crystals are sharp-edged and cubic as expected. As the weather was too hot, evaporation was fast, which is why they aren't completely transparent. Now, let's talk about the solid-state physics behind the structure of sodium chloride crystals. Sodium chloride, or table salt, forms a very specific type of crystal lattice called the face-centered cubic, or FCC structure. This is one of the most efficient ways for ions to pack together in 3-dimensional space, and it's incredibly stable. Let's break this down. In the FCC structure, the sodium ions and chloride ions alternate positions in a repeating pattern. Each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. This arrangement forms what's called a cubic coordination, where the ions are symmetrically distributed to minimize repulsion and maximize attraction between oppositely charged ions. The octahedral structure, as shown in the middle image, highlights this coordination more clearly. You can see how the ions are arranged geometrically around each other. This arrangement ensures a very strong ionic bond, which is why sodium chloride crystals are so stable and hard. When we zoom into the unit cell, which is the smallest repeating unit in the crystal, we find some interesting details. In the FCC structure, there are 4 sodium ions and 4 chloride ions per unit cell. We calculate these by considering how ions are shared among the edges, corners, and faces of the unit cell. For example, a corner ion contributes 1/8 of itself to the unit cell, while an ion at the face contributes half. This structure is why sodium chloride crystals form their characteristic cubic shape. The symmetry of the lattice is reflected in the macroscopic crystals we observe, especially when grown slowly to allow the ions to arrange themselves perfectly. Overall, the crystalline arrangement is a direct result of the balance between the attractive and repulsive forces in the lattice. It's a fascinating example of how solid-state physics governs the structure and properties of everyday materials like table salt. But how do the crystals form? Crystallization happens when free-moving ions in the solution collide and interlock like puzzle pieces, arranging themselves in a lattice structure, making a crystal nucleus. As more and more ions join the nucleus, it grows too big to be in solvent condition and will fall out of the solution as a crystal. Other ions in the solution continue to join the crystal and the crystal grows. Here we can see a real-time video from the University of Tokyo on how the crystals form in ordered lattice structures. Now that we looked at how they form at a molecular level, let us look at the factors that affect crystal formation in practice. Firstly, the rate of evaporation. If water evaporates slowly, larger crystals tend to grow. The crystals will also become increasingly more opaque with faster rate of evaporation, which is why my crystals were not completely transparent. Temperature also affects the crystal formation, as slower cooling tends to result in large crystals. Another thing that affects it is the concentration of salt. The solution has to be supersaturated for larger crystals to form faster. Lastly, the purity of water affects crystal structure. Any impurity would invade the lattice structure and the crystal wouldn't be cubic. Well, that brings us to the end of the video. Thank you for watching this far and I hope you enjoyed the video.